So in this video, I want to talk about Gauss's law. So Gauss's law is this formula, and it's basically just saying that the net electric flux, sorry, this is electric flux. So the electric flux going through a closed surface, so that's what the circle on this integral represents, is closed surface. So the electric flux due to the charge enclosed by that closed surface. So this is the I should say the net electric flux due to Q enclosed in that closed surface is equal to the electric field produced by that closed surface over each part of its surface dot. So this is a dot product of dA, which is the infinitesimal area vector, and I'll show how this equation works, which is equal to the Q enclosed over epsilon naught. So first of all, epsilon naught is a constant. It's just equal to 1 over 4 pi k being Coulomb's constant, and it's about equal to 8.54 times 10 to the negative 12th, and it has the units Coulomb squared over newtons times meters squared. So that's its units. And so Q enclosed is net charge enclosed by whatever surface you're using. And so the surface that we use is called a Gaussian surface. So by a Gaussian surface. And so I'm going to illustrate this all through example. So Gaussian surface. So a Gaussian surface is literally just any imaginary surface that you come up with. It doesn't affect the electric field or anything like that. It's just sort of like this bubble you could imagine. You can make it a cube, you can make it a cylinder, you can make it whatever you want, and it's just so that we can talk about the electric flux. So as just a starting example, so let's say I have some closed surface, and again, so a Gaussian surface is always a closed surface, meaning that there's no way, if you imagine the surface is hollow, so there's no volume on the inside, no material on the inside, there's no way to get from the inside to the outside. That's what we mean by a closed surface. So there's no holes in it or anything like that. If you had air inside of that volume, there would be no way for it to escape. So that's what a closed surface is. So if I had some wacko closed surface like this, and I said that I have this point charge right here, Q. And so Q is equal to 5 times 10 to the negative 5th coulombs. And I ask you, I say, what is the electric flux of this surface? You know, in this case, it would be exiting the surface due to the charge enclosed by it. Well, the net charge is just Q in this case. So we have Q enclosed equals Q. And so then, just from this above formula, we don't even actually have to use the integral. It's just Q enclosed over epsilon naught, which in this case would be 5 times 10 to the negative 5th over epsilon naught, and you would just plug in this constant for epsilon naught, and that would be your answer. So if you did another similar example, so you had another really weird closed surface, right? And we're assuming that this is 3D, so this is some 3D surface. A closed surface is a 3D surface, and so we have another Q here, but now we have a negative Q, and I ask you, what's the electric flux due to these charges? Well, the Q enclosed is the net charge, which is just the sum of the charges, right? So the sum of negative Q is minus Q, which is 0. So the electric flux is Q enclosed over epsilon naught, which is 0 over epsilon naught, which is just 0. So there is 0 electric flux leaving this closed surface, or I should say the electric flux of this closed surface is 0, even though it does actually, even though it does have charges within it. It's just the net charge enclosed by it is 0 in this case. And so you always want to be careful. Q enclosed is the net charge. So you want to add the charges, including the signs for the charges. So, and let me just shift this around a little bit. Okay. So, and then now let's actually give an example involving this integral for Gauss's law. So, I'm just going to do one example involving the integral in this video, just to sort of illustrate what I'm talking about with this integral. So we said that the magnitude of the electric field, we can draw the absolute value bars and the vector sign over it, or we can just draw it, write it like this, just as the variable. So E equals kq over r squared. We said that this was the equation for the electric field, the magnitude of the electric field due to some point charge, where q is the magnitude of its charge, k is Coulomb's constant of 9 times 10 to the ninth, and then r squared, with just r being the distance from that point charge. And so we can actually use Gauss's law to show that this is actually the case of, that this is actually the magnitude of electric field for a point charge, derived using that integral that we have above. So let's imagine we have some positive point charge, and it's got all these electric field lines leaving it, right, radially outward in all directions. So I don't want to be too sloppy here, right? So something like this. Now I want to use Gauss's law. So we have to pick a Gaussian surface that exploits the symmetry of the charge source, which in this case is just a positive point charge. We see, if we imagine this in 3D, these electric field lines are coming off. It sort of is like a ball with a bunch of spikes coming off of it. So to exploit the symmetry, we're actually going to use a Gaussian sphere, meaning our imaginary closed surface is just going to be a sphere. So in 2D, this all looks like a circle and all that, but this orange thing is our Gaussian surface, and it's actually a sphere here. So first of all, let's how do I want to do this? So let's just start by writing Gauss's law. So we have this guy equals q enclosed over epsilon naught. I want to emphasize that this is a subscript. So q enclosed over epsilon naught. So we want to imagine what the magnitude of, because this is a dot product, right? So let's first remember what a dot product means. So if we have a dot b, it's the magnitude of a times magnitude of b times cosine theta, theta being the smaller angle between them. So we could rewrite this integral as the magnitude of e times the magnitude of a times cosine theta, which is the angle between them, right? And so let's imagine the electric field. So the electric field at all of these points is coming radially outwards, right? At all of these points, it's coming radially outwards. And so dA, this infinitesimal area vector, is just some infinitesimal area. Let's say if let's do it in purple, or actually we'll use this green color. So this is dA, so we'll say it's like some infinitesimal portion, and it's actually a vector. So it's actually this little green vector that points out for this little green area. It's an infinitesimally small portion of our Gaussian sphere. And so what we want to do is we want to simplify this. So E, we assume, is going to be constant all over our Gaussian surface, because the Gaussian surface is a sphere with its center at the positive point charge. And so we also know the equation for the point charge, but just conceptually, we assume that the magnitude of E is going to be constant, be all over this Gaussian surface, because everywhere on the Gaussian sphere, it's going to be the same distance from the positive point charge inside of it. So if I just want to simplify this slightly more, I'll keep using my orange color. So we can pull E out of this integral. Cosine theta equals q enclosed over epsilon naught. Now, cosine theta, what is the angle between, so this green guy is dA, and then the pink one is E at that point. So what is the angle between E and dA at every point? And by the way, dA, so there's always two directions for dA. It can point inwards or outwards, perpendicularly outwards or perpendicularly inwards. Whenever we have a closed surface, the dA always points outwards, away from the inner volumes. That's how I knew it was this direction. So anyway, so everywhere along the Gaussian sphere, the angle between E and our dA is going to be 0 degrees. So we have that theta equals 0 degrees everywhere, right? As you know, all over this Gaussian sphere. And so what this means is that the cosine theta in our integral is just going to become of cosine of 0 degrees, or radians, doesn't really matter, both are 0. And what is cosine of 0? It's just going to be 1, right? And then now I ask you, so what is the integral of dA? What is the total area? What is the area of all the dA's added up? Well, it's just the area of our Gaussian surface, our Gaussian sphere. And so that's just going to be the surface area of a sphere, which is 4 pi r squared. So we get that our electric flux is E 4 pi r squared. And so I'm assuming this guy has a radius of r is equal to Q enclosed over epsilon naught. And so I'm going to ditch the the electric flux variable, because we're actually using this to solve for the magnitude of the electric field due to the point charge. So from this, we just have this, right? And we can write epsilon naught as 1 over 4 pi k. So I'm actually going to do that first. Over, and then 1 over 4 pi k of 1 over 4 pi times Coulomb's constant, which just becomes this, Q enclosed, so it's going to be 4 pi k, Q enclosed, right? And so now let's divide both sides by 4 pi r squared. So then the 4 pi's end up canceling out. So we end up with K, Q enclosed, and hopefully this is looking familiar. And then what is our net charge enclosed? Well, it's just the charge of this positive charge, which we'll say is just Q. So we just found that the magnitude of the electric field due to a point charge, and actually it works whether the point charge is negative or positive, is KQ over R squared. And we already knew that, but we just derived it using Gauss's law. And so Gauss's law is really powerful for deriving the magnitude of the electric field due to various charge sources, be they like point charges, or like we have infinite cylinders of charge and infinite planes and all sorts of interesting things like that we can find the magnitude of the electric field due to. And so conceptually, Gauss's law, I hope is not overly complicated. It looks like a lot of math, but conceptually, we just said that the electric field was going to have a constant magnitude over our Gaussian surface, which is an assumption that we often do make based on the symmetry that we pick for the problem. So we just pull the E out, and then we just have to figure out what the theta is between E and dA. And so usually we assume it's going to have a constant angle over the entire Gaussian surface, which in this case is 0 degrees. So that just simplifies the dot product. And then you just have the integral of dA. So dA, and then it's just which is just the total area of that surface. So if we wanted to write it in one step, what we had here was E dA, right? And then this became the dot product. We knew that the angle between them was 0, so then this just becomes E dA in terms of magnitudes. So we pull this out, and then this gives us the total area, which is just E equals 4 pi r squared, the surface area that is. So this is sort of a more condensed version of what I did over here. So anyways, I hope that is helpful in coming to understand Gauss's law.